Good morning, dear students. Welcome to a session of Communication Lab. So in the previous sessions, we discussed regarding usage of Simulink for simulation part of the experiments which are present in Communication Lab. So in this session, we'll be discussing regarding few of the hardware experiments from theoretical point of view. So and we'll be looking forward how we can utilize those for implementation of specific purposes. So in this session, right, we'll be basically looking forward for using, we'll be referring to frequency shift keying and phase shift keying. So these two are actually the digital modulation technique. Now, on what basis do we classify the modulation to be digital? It is all dependent on the message signal or the message or the information. If the information is in the form of ones and zeros, that is, it is in the form of bits. And using this bits, if you perform the modulation, then that modulation will be classified as digital modulation. If the data or the message signal is in the form of analog and you use that analog information to do the modulation, then we classify that modulation as analog modulation. So in this session, we'll be concentrating on FSK and PSK. Then apart from that, we'll be discussing another one technique, which is multiplexing technique. So that is basically referring to the multiplexing in the time domain. So let us move ahead. So the first point what we need to discuss is FSK. So what is FSK? FSK is frequency shift keying, and it's a digital modulation technique. Digital modulation technique. Now, why it is digital? Because the message signal, what is used for modulation is actually binary or bits, or it is in the form of zeros and ones. Now here, what we are doing is we are representing data over here. So this data is either, so we also refer it as logic low and logic high, low and high. So this is high, which is nothing but it is logic 1. This is low, which is nothing but logic 0. So here we are having a sequence of ones and zeros. So this is the message signal, which is nothing but the bit stream. It is the bit stream. And next we have the carrier information, which will be modulated based on this message signal. It will be modulated based on the message signal. Now, how will the modulation go ahead? Now here, since the only two possibilities are data will be either 0 or 1. The bit stream can be either 0 or 1. So with respect to that, what should happen to the frequency of the carrier? So this is the carrier signal. So what should happen to the frequency depending on the data what you are considering? So logically, what you need to do is whenever data is 0, you send, say, a low frequency version of the carrier signal. That is, you change the frequency of the carrier to low frequency. And whenever the data is high, that is logic 1, you change the frequency to high. That is, you increase the frequency of the carrier signal and then use it. So that is what is done in this modulation over here. So here we can see that this is the bit period. So in the given bit period, what happens is you need to check whether the data is 1 or 0. So in this case, the data is 1 for the entire bit duration. So what is done is in this entire bit duration, you can observe from this point to this point, the frequency of the carrier is kept high. So in this case, so I'll be considering that this frequency itself is higher and then we'll be sending the same signal. So I'll not be altering the frequency of the signal and I'll be sending the high frequency content of the carrier signal. Now, what happens if the data is low in the given bit interval? So in this case, we can observe what is happening. So in when the data is low, right, what happens is the frequency of the carrier gets reduced. So this is the concept what you have to utilize when you're implementing FSK. When you're implementing FSK, and this process repeats in the further coming the bit streams. That is, if it is one, again you consider the high frequency. Here you can see that in the bit duration, again high frequency signal is being sent, and when it is again zero, low frequency signal is being sent. So this will continue for the rest of the bit streams. The advantage is that you will be having only two possibilities: either the data will be 0 or 1. And when we are representing this in the voltage representations, as we had discussed in the previous case, we can represent it in NRZ, RZ, return to zero, non-return to zero, binary, polar, unipolar. So all those things can be considered. So this is actually the representation what they have displayed over here. So it is, so we can consider it as unipolar, non-return to zero format, what they have considered. So here they are representing that. So logic 1 is represented with high voltage for the entire bit duration, and logic 0 is represented with 0 volt for the entire bit duration. So it is actually non-return to zero unipolar format. So you represent this. So here what happens is only two possible values, that is 1 or 0. Therefore, only two possible voltage representations. That is, it will be either plus V volts or it will be 0 volt. So based on this, you change the frequency of the carrier. But what happens to the other parameters of the carrier? The other parameters of the carrier are unaltered. So you can see that the amplitude of the carrier is unaltered and the phase information pertaining to the carrier is unaltered. Only parameter which alters is the frequency. So therefore, this technique is termed as frequency shift keying. So how do we implement this in the hardware aspect? So we can make use of different devices in order to implement this. So logically, what we are looking out, whenever data is 1, you send the high frequency signal. Whenever data is 0, you send the low frequency signal. So this is the logical aspect what you have to implement. So how I can implement this? I can implement it by using different switching devices like MOSFET. Then we can use the transistor, we can use the 555 timer. So other this thing we can use 8038 IC. So these are few things what we can look forward. So in this one, what we are doing is we are using a MUX over here. That is a multiplexer. So using CD4051, we try to implement FSK. So before going into that, we should know what are the details pertaining to CD4051. Now, CD4051 is actually a MUX DMUX IC. It is actually a MUX DMUX IC. So it can perform multiplexing and demultiplexing operation. Now, when we are considering this, so this is the pinout what we can observe for CD4051. So before using this, you should know what each pin is used for. So here we have the supply which is given to pin number 16, VSS which is the ground which is given to pin number 8. And here we can see that there are three control pins. So these are nothing but the select lines. These are nothing but the select lines. So in MUX and DMUX, you have a select lines. So these are referring to those select lines. So based on what is the combination of ABC, if it is say 000, what happens is I0 will be selected. If it is 001, I1 will be selected. So in this way, you can have up to 111. So if we can have 01 up to 7, so I can have total of 8 input pins in the multiplexing operation. 8 input pins in the multiplexing operation. Now the same pins can be utilized for demux operation. So when we come across with that operation, we will observe how it is being utilized. So here you can see they have given few specifications. In out 0. So it is the I naught pin. This is in out 3. This is I3. This is I1. This is I2, I4, I6. Then we have I7, I5. So these are the 8 pins which we have for the multiplexing and demultiplexing operations along with these 3 select lines. These 3 select lines. So let us observe a few of the things. Other pins will not be utilizing, and pin number 3 is actually operates as the input or the output pin. And here you can see that all are in out. So it implies that these pins are bidirectional. Either you can send the signal into it or you can receive the signal from it. So when it is acting as a multiplexer, this pins will be accepting the input. When it is acting as a multiplexer, these pins will be acting as the output. These pins will be acting as the output. So therefore, we can observe that these pins are bidirectional in nature.